there are any questions. Any questions regarding last tutorial that we had last week. And today we're going to, should see my screen. And today we're going to start discussion about stochastic signals and correlation and power spectral density for stochastic signal. I'll be ready and start. And we start our discussion with first task number 4.1. And I believe you start discussion about stochastic signals lectures, yeah? And we just going to solve examples that will help you understand better what it's about. So we start with task number 4.1. We consider a discrete time random process, x of n. All random variables x of n are assumed to be statistically independent and identically distributed. It holds that x of n belongs to the, for x of n, we have finite alphabet, which 4 symbols, -3, -1, 1, and 3, where all states are equally probable. And then we have multiple questions. First, we need to determine autocorrelation function. We need to determine what's the probability, what's the power spectral density. And in the end, we have to repeat, we have to find autocorrelation function and find probability density function for slightly different alphabet. Look to original alphabet, you see that you have 2 symbols with minus sign and 2 symbols with plus sign. So it's called unipolar. Bipolar. Well, actually for bipolar, you have only 2 options, but anyway, it's kind of bipolar sequence. While in the end, we have to consider bipolar sequence because all symbols have only positive sign. Then we try to analyze what happens if we have such alphabet. Okay, so we start in a second. And you can ask questions before we start. You can always ask questions. Okay. Started, and this is a code time modulation for 4.1. Time modulation. And for modulation, we have both x of n belong to -1, 1, and also say that adjacent symbols x of n are statistically independent. So, first question, we need to determine what's the autocorrelation function. Such this, we phi x n. Okay, let's see. This first question. We can all unrelated questions we discuss in the end of it. Okay. Autocorrelation function. And autocorrelation function, phi x of not actually n, but the function of m, because n is index of our symbol, and then we have to specify when we calculate autocorrelation, we calculate correlation between 2 sequences, original sequence and then shifted version. And then this index m specifies what's the difference, what's the shift between these sequences that we have. So, and we have the following expression to find autocorrelation function. Phi x of m have 2 options. So, how do we calculate autocorrelation function? Rectangular. Well, yes, you are right, but it works for periodic signals and for finite signals. But here, we're talking about random signals, random. Of course, you can write this sequence of data, but only one realization out of infinitely many others. And here you have to somehow calculate average over of something. Other ideas? I think you should discuss it during lectures. Yes, it's almost right. I mean, you said very important note, expected value. And here, actually, we do, now we have to combine two answers. We have to take this tabular form and expected value. Actually, what we do, just imagine that if you have m equals to, and on the right side, I just show you are just random sequence of symbols. This random sequence, absolutely random. No any reason why it's like this. You can just draw your own, it's absolutely random. And then if you calculate autocorrelation for shift between this sequence and the same sequence but shifted by 0 symbols, right or to the left. But actually what happens? And copy this picture, put it below, and maybe change color. Let it be. Okay, now we have another sequence. And then what actually you do when you calculate autocorrelation for shift equals to multiply, calculate square value of your sequence, and then calculate and then average over all results. And if I do this here, get that I have first time it will be first part it will be product gives me 9, product gives me 1, 1. Some point actually we should get have either 1 or this nothing else as paired original sequence. You just take sequence x of n, you calculate square value of each symbol that you generate, Then for autocorrelation function of stochastic signal, you calculate expected value, as you said, yeah? And then if you calculate expected value of squared random variable, what it is? Squared value of random variable. And you have sorry?
Total power.
Yes, I mean, well, I mean, yes and no. It's related to power, but actually in terms of random variables, you have zero mean, you have variance. But if you have non-zero mean, we call it as second moment. Second moment. This is parameters that characterizes random variable. And this is what actually we write on the left side, that when m equals to 0, you just need to calculate second moment. Oh, actually that we have times m. So let's change something in. Oh, let's change it to L, because otherwise it times m. L. Not conceptual problem, but just both cases something goes. So we just say that our autocorrelation function is function of L. L is different than small l. And then when you shift your sequence, by any arbitrary number to the right or to the left, it will happen that you calculate product between statistically independent symbols. As a result, autocorrelation can calculate, in order to find this autocorrelation, you calculate squared value of first moment. First moment where L non-equal to 0. But it works only if your sequence are independent. Because if your sequence is dependent, then you have to take this into account. But for this task, it works perfectly. You have independent symbols, and autocorrelation function can be found as this. L equals to 0, you find the second moment. For L non-equals to 0, you find square. Now we need to find both parameters. Okay, so now let's try to calculate what actually we get. Phi else. Any questions? Phi xx of 0. And calculate, in general, we have expression expected value of x conjugate x, because your symbols may be valued. Yeah. In this case, we don't need conjugate, but I still write it just general expression. Since this expected value, this second moment, we can find as summation of probability of symbol times x of n conjugate times x of n. Then we just need to calculate sum over all possible symbols in our alphabet. So, say that all symbols independent and they have the same probability to appear in our stream. Then my question, what's the probability that you get symbol, let's say, -1? Well, no, if it's 0, then you never get it. Yeah, it's 1 by 4. I mean, you have 4 possible options. -3, -1, 1, and 3. And then all of them tends to appear, and it means that you have just the same probability for each of them. Then you have 1 by 4. And you already have everything what you need to find this autocorrelation function for 0. Because you said that probability for one symbol is 1 by 4. Then what's the value for one symbol? Oh, no, not correct. What's the value for each symbol? We just write it. For one symbol, we have -3. plus another symbol has the same probability but different value, -1, plus 1, plus 1 over 4. This is how we calculate second moment. Now we just need to, now we need to calculate this expression. Have 9 plus 1, it will be 10, plus 10, 20, divided by 4, it will be 4. 0, point equals to 0, our autocorrelation function equals to 5. And this is, I would say this is average power that we transmit. Yeah, this is average power. But I mean, you, of course, you have random sequence, but if you measure long enough this sequence and measure power, on average, you get this 5 in terms of, I don't know, volt square over time or whatever. So this is first part. Then we go to next part. Now then we need to determine what's the autocorrelation function. What's the autocorrelation function for non-zero? On this one. This one. This is definition of second moment. I mean, this is actually what we did, because you have, in our case, we have real valued signal. And then we just say that we just calculate square value. Just this resulting sequence is you just take your x, calculate square, and you get squared sequence. But in general, you should take into account that your constellation might be complex valued. And then for complex valued constellations, we not only absolute, we take not only square valued, but in addition we take absolute value. And then you remember that for absolute value squared of a complex number, you can represent it as heat conjugate times z. So this is nothing. This is inside expected value. This is nothing else as x absolute value squared, and of course, then we just represent it as product between conjugate and x itself. Yeah, and then you just plug everything what you know about this sequence, and okay, yeah, of course I had to write absolute value squared, but it's real value, square value, and then yeah, then get this answer. Okay, yeah. Questions? And we just continue for any other point, for point L that's not equal to 0. Then, because we say that two symbols statistically independent, you remember that expected value. I mean, actually, we use exactly the same expression. We use expected value of x of n conjugate times x of n plus L, because now we have shift between sequences. But because we say that these sequences are independent, what happens? No, not 0. Only for this specific example, it will be 0. But I want to say that this expression, because we have statistically independent, we represent as expected value x of n conjugate times expected value of x of n plus L. A product of two expected values. But then, of course, if you take this specific alphabet and calculate expected value, it will be 0. But only for this specific case. And you know it's not true. Not necessary. So, and questions? Okay, we have another example in 5 minutes, and then we see what happens. Let's see, I mean, maybe, but let's see. Suppose. Sometimes it's like a miracle. Let's try to calculate first this for this specific case when we have L. And then what's the expected value? We have probability for each symbol, and then we calculate -3. I just put probability outside parentheses, and inside parentheses I have -3 -1 +1 +3 times, and then actually we can just write the same, or I will write square. But you see that inside parentheses you have 0. As a result, for this specific case, this autocorrelation function equals to 0. And also you can do it explicitly. You can just take your sequence x of n. You can write all possible outcomes for this sequence, -3, -1, 1, 3. Then you take sequence x n plus L. I mean, it means that you just take another symbol. And what's the possibilities for the second symbol? All the same options. -3, -1, and 4 can be -3, 1, 1, and 3. I want to say that first symbol, you transmit first symbol -3, second symbol, maybe one of these all options. If you transmit first -1, again, you have for second symbol all possible options. Then for each first symbol, you have don't know what it is. Then if you take, if you calculate these pairwise products, and calculate sum over all possible outcomes, you will get 0. Should get 0. I would expect. But okay, but actually what we do. And shifted version of our sequence. Probably it's time to give microphone. Pass the microphone. And at the same time, I will try to switch on. Okay.
Hola, hola, hola.
Okay, yeah, it works. Oh, now people from WebEx also can understand what happens.
No, I'm just asking that if the autocorrelation of the first moment needs to be the x of n conjugate multiplied with x with the chief of L, but at the like the square version, because we are talking about the first moment. If you go up in the assumption that we made, the autocorrelation.
This one.
Exactly.
Yeah, but this is actually what happens. This is you calculate this second moment, but you have independent symbols, and then what it is here? The first moment. Same. This is also first moment, but we say that we have stationary random process that parameters doesn't change, yeah, and then regardless of shift, you have the same statistical quantity, and this is exactly this is first moment. Hope it's fine. So let's go further, and now we need plot this autocorrelation. Now we have to plot this autocorrelation function as function of index. Actually, it's 0 have this pulse, amplitude 5, all other in have 0. Minus 3 and so on. Our picture. So, and for equation, you can write that this phi xx of L equals to 5 when L equals to 0, and equals 0 when L not equal to 0. What you can write. And now we go to part B. Part B. Part B, we need to determine power spectral density. And for power spectral density, we so-called discrete time Fourier transform, because now you need to go from discrete time to continuous frequency. And for this reason, you use special transform. And I write how it looks like this. Power spectral density, continuous time, we can find as sum of discrete exponential components. Exponential pulses. M goes from minus pi xx of L times exponential term minus pi f L t 0. And this is how we actually, no, it's not pulses, it's exponential in general, exponentials in frequency. Because what actually we do, now we substitute all what we know. And if we look to autocorrelation above, we see that we have actually only one non-zero component. And we can write that our autocorrelation, our power spectral density is, just write what we have for 0. 5 times there minus G F times 0 times T0. Without exponential just forms into 1. And we get that our spectral density is a constant function. Our business as a line goes from minus infinity. But also we should take into account that our original sequence is a discretized version of continuous process. And have for discretization, we have sampling frequency or sampling interval. 0 is sampling interval. And 0, it's sampling frequency. And we have to specify somewhere on this plot this sampling frequency, or actually sampling frequency over 2. Say sampling 2. Just arbitrary, you just specify that somewhere, you just by yourself, where is the sampling frequency? Because you have to specify, otherwise it's not clear how you go from discrete time to continuous and vice versa. Okay, that all? And no, not all. Now we have part C. Part C, we have to repeat all the same steps, but for unipolar sequence. So now we say, have unipolar x of n belongs to the alphabet. And it was a question from one of you, yeah, that what actually happens. And now we see what happens in this. We just try to do all the same. We assume that the sequence consists of independent symbols. And to find autocorrelation function, first we calculate autocorrelation for 0. And we need to calculate second moment. So, I mean, probability again will be the same, 1/4. And then we need to calculate square value of each symbol. 1 square plus 2 square plus 3 square. Okay, what will be the result? (14/4). Or we can say 7/2. 14/2, 7/2. And then we just continue and we need to find what will be the answers. Oh. So we will find out a correlation for L. And then all the same, we need to calculate, instead of second moment, we need to calculate square of first moment. For first moment, we calculate 1/4. Then we have summation of all possible symbols. 1 plus f square. What will be in this case? By 4. See that we have different result. Previously, it was 0, but now it's not 0 value. It's 9/4. And it means that have specific correlation between symbols. You have correlation. Transmit very long sequence of symbols. And if you just take symbols from different positions, calculate what's the correlation, they will have correlation between these two symbols, always. Because in general, you have 4 sequence, and you have, it means that you have DC. You transmit, you spend DC, have to transmit DC component. Okay, and first we need to put out the correlation. Try to find power spectrum density. So have pi x. Have 7/4. Actually, it's better if we use the same denominator. Let's say now our 14/4, then some over. The correlation is quite high, or any. Value is by 4. Now we need to find power spectrum density. Our write it as summation goes from minus infinity pi x L exponential part f, and actually try to analyze what we have. find power spectral density. We can represent first discrete pulse as sum of two components, as this part with amplitude 9/4, and the residual part with amplitude 14/4 minus 9. It will be this residual will be 5/4. Then actually interesting. You can observe interesting. Something interesting that you have this sequence of delta pulses. Sequence of delta pulses, discrete time. If you calculate Fourier transform, inverse Fourier transform of sequence of discrete pulses from discrete time to frequency domain, then what do you get? Actually, this kind of constant in continuous time. In continuous time, you would have constant, but then you sample it and you get just sequence of samples. What happens if you calculate this Fourier transform of a constant? Get delta pulse. Delta pulse. And what happens if you, so now what we know what happens with this part, that we just take the if we take inverse Fourier transform of these delta pulses, we get, if we take inverse Fourier transform of discrete pulses, we get delta pulse at 0. And then if we take only one discrete pulse and calculate Fourier transform, we already did it before. What do we get? Constant. Now we just need to combine these two observations. And by the way, we have additional caveat because what can you say about spectrum of discrete sequence of samples? Oh, anything, or do you have anything special about discretized sequence of samples? Digital spectrum. What's wrong with digital? It's periodic. Yeah, this is a problem that it's periodic. And then we have to continue our result, or just what we get, infinitely many times to the left and to the right. Try to combine all this stuff that we So first of all, at 0 pulse spectrum, and this magnitude 9/4. And we have, in addition, constant component amplitude, write it some 5/4. But then I also arbitrarily specify that this is our Fs/2. I specify this range so that the beats you Fs. And then how should I continue spectrum? Where should I place another delta pulse? At which frequency? Say that it's periodic. And if it's periodic, second period, how we should it? Or what's the period in Fs? Yeah, this is the answer, that if you have delta pulse at 0, then next period will be at Fs. And then 2 Fs, 3 Fs, and then up to infinity. I just specified that we have S. Of course, constant level goes just everywhere. This. Also, this is how we find power spectral density. This is a feature of this result that it will be periodic, because original signal was discretized. Okay, and we can write that idea to find the power spectral density was the fact that we have just sequence of discrete pulses, and this is approximation of a constant level. And result for this of delta pulses after discrete time Fourier transform. We get constant level amplitude pi over 4. And for the remaining part that we have at 0, amplitude phi over 4. Oh, sorry, it was wrong what I said. We have this sequence of delta pulses, and after Fourier transform, of course, you get delta pulse, not the constant level. You have delta pulse with magnitude 9 over 4. And for the remaining part at origin and amplitude phi over 4, after discrete time Fourier transform, you get constant level, amplitude phi over 4. How we get. And in addition, we say that original sequence was sequence of discretized samples, autocorrelation of discretized sequence. And for this reason, our power spectrum density will be periodic, period Fs. Then if you have at origin delta pulse, you have to repeat this delta pulse with period Fs, right? And that's the way how we find resulting power spectrum density. Pi over 4. Because you have this difference, remember that at origin, you have discrete pulse with amplitude 14 over 4. And then if you just remove this delta pulse completely, for this Fourier transform of this sequence, you don't get one delta pulse, because for delta pulse, you have to have discrete pulse at origin. And in order to get this delta pulse at origin, decompose our delta pulse with amplitude 14 over 4 for two smaller parts. We decompose it and we write that 14 over 4, nothing else as 9 over 4 plus 5 over 4. And this 9 over 4 comes as a one part at origin of this sequence of the remaining delta pulse. But then you have remaining component, you have this phi over 4. And then what happens after inverse Fourier transform of this 5 over 4? Comes to constant. Yeah, and this is how we get this result. We just for two parts, and then you just what happens with each. Okay, yeah. And at 0, it goes to plus infinity. I mean, it's everywhere constant, but at 0, it goes high. Because, I mean, of course, for practical implementation, then you approximate delta pulse as pulse with very high amplitude. Then it will be just something like spikes in spectrum. But I didn't show you this because it's not theory, it's what you see in spectrum analyzer. It also depends on the resolution of yours. So let's go further and That's all for part for first task. Another question. Yeah, of course. Yeah, I mean, should distinguish statistical independence and correlation. If you have independent sequence, it doesn't mean that it's uncorrelated. Independence tells you that if you observe one symbol, can you predict second symbol? And answer no, I mean, because dependent. But if you observe one symbol, do you know anything about correlation? Yes. Because I mean, amplitudes, all of them have positive amplitudes, and with they have correlation. But you don't know what will be what will be the next value, even current observation. Distinguish correlation and independence. Well, they correlated, but I would say highly correlated, but independent. Okay, other. Now we go to question 4. So, and for this task, we consider a discrete time filter with the impulse response geo, according to the figure. Our time filter response. And a random discrete time binary signal x of n is applied to the input, where x of n belongs to the alphabet -1, 1. All states are equally probable. Successive states of the sequence x of n are statistically independent. Then we need to find equation of the filter transfer function using EFT. Then we need to determine call it as if we have any just absolute value squared of transfer function. And then we need to find plot the probability mass function, not all. Then we, just start trying to find autocorrelation function. Okay, let's start task. Try to solve it. First, I show how our discretized impulse response looks like. At 0, we have pulse with amplitude 1. And then at 2, we have pulse with amplitude 2. We should be careful about it. 1, 2. So, and this is n. Size impulse. Now we need to find power spectral density. Find how to call it transfer function. Function g of f. But we use same idea. I mean, just say that this g of f is summation goes from minus. I should use n of n times exponential function minus j f times t0 sampling interval. So, and just substitute everything what we know about this filter. Know that at 0, value of impulse response equals 1 times exponential minus y times t0 and minus 1 at position have exponential y and t0. Say that t0 is proportional to sampling interval 1 over fx. And write that as first term of course will be 1 minus exponential function y t0. our transfer function. Function, nothing special so far, but okay. And then we need to find what the absolute value squared of this transfer function. We have to find 1 minus j 2 is 1 minus exponential function minus j. As it is. Then what happens if we apply conjugate to the first parenthesis? Does it change how our bonus? Conjugate. Conjugate what? Yeah, it change sign of our exponential, argument for exponential function. But it change sign only if you have complex numbers there. I mean, what happens if you have exponential of alpha conjugate? Yeah, I mean, because this will be exponential alpha, but what if I have j alpha? It will be exponential minus g alpha. Yeah, I mean, it should be very, very. Then I write that for first parenthesis, we have 1 minus exponential plus g 2 pi 2 t0. Second, we have minus 1 minus exponential minus 2 pi 2. Get f, yeah. I forget to write f. Point. Thank you. Yeah, please pay attention. So how can we simplify this expression? I propose to do the following trick. We move outside first parenthesis, exponential j 2 pi f without 2, and from second parenthesis, oh, sorry, this minus, we move from first parenthesis, exponential minus j 2 pi f t0, and from second parenthesis, we move outside exponential j 2 pi f t0. Actually, let's happens. No. We should actually move plus, because then we do exponentials. Exponential g pi f have exponential minus g minus exponential. Have to move with this plus sign. From second parenthesis, we move outside exponential minus g pi f t. Side we have exponential j 2 pi f t0 minus exponential minus j pi f t. What we get, and we see we can cancel exponentials outside parentheses, and what we have inside parentheses. There is actually a hint in the task. You don't have this hint task, but anyway, you remember that exponential term we can represent exponential j alpha. You can write as cosine j alpha, cosine alpha plus sine alpha, exponential minus j alpha. You write as cosine alpha minus sine alpha. As a result, difference of these exponential terms. Sine alpha. I think it will be minus 2j. This one, this. Ah, yes, yeah. J. We have j, but now I'm talking about this expression for resulting. Minus 2j sine alpha. Minus 2j sine alpha. And for second parenthesis, I mean, it's exactly the same, but with different sign. 2j sine alpha. So, and then if we calculate product of these two parts, we get that we have j times j will be minus 1, 2 minus 2 times 2 will be minus 4, times minus 1 will be 4. We have 4 times sine, and we write that we have 2 pi f t0. Have this our transfer function. Sine square, of course. Square, yes? Are you talking about second part? Yeah. So this should be 1. Moving outside, okay, if you look to the expression previously, we have 2 times t0. And what I move 1 times t0 outside. So one part you still have there. So let's go further, and what else we need to find? Now we need to consider, do we need to plot this? Don't need to plot it for now, but probably we do it later. Consider what values the random signal y of n can take at the output and sketch the corresponding probability mass function q of y. Have to find what will be the output of this system. And we can do the following. We can consider all possible options for signal x of n. Then we can also try to consider what we have for sequence xn minus 2. And finally, try to find what will be the result y of n. So, and because these two symbols independent, we just need to try to consider all possible options. So we have for first signal we have 1, for second also 1. For first we have 1, for second minus 1, for first minus 1, for second 1, and for both of them we have minus 1 and minus 1. What happens if we have first sequence 1 and 1? We just what we do? We take our current signal x of n and subtract the signal from the past, from time samples ago. And if we do this, this difference will be equal to 0. And we take second option. Just copy again. what we take current symbol with amplitude 1 and subtract 1 amplitude minus, or we add with amplitude minus 1. So now we have 1 minus minus 1. So it will be 2. Then we have minus 1 minus minus 1. Minus 1 will be minus 2. And minus 1 minus minus 1 will be 0. Okay. And then if we get such possible outcomes for resulting sequence y of n, what will be the probabilities for the resulting symbol? So as I see, as a result, we can have 3 possible outcomes. We get 0, we get 2, and minus 2. So what's the probability that we get 0? Come louder. 1 by 2, yeah. And what's the probability that we get, say, minus 2? By 4. So, and based on this, we can easily plot the probability mass function. So this says we have sequence y of n. Oh, no. This is y of n, possible amplitude, our mass function. And we say that for 0, let's say we have probability 1 by 2. For possible outcome 2, we have probability 1 by 4. For minus 2, we have also 1 by 4. This is our probability mass function. What else we have? So y of n means that like possible amplitude. Not function of index, but it's in general what's the possible amplitude for the resulting sequence. So let's go further. You have to explain in single sentence why it's dependent on the time index. Hold. Answer, I wrote that dependent, but we have a resulting sequence. Go to part E. Yes. Just go through all possible combinations. Have full alphabet with 2 symbols, 1 and minus 1. And in order to understand what... Okay, yeah, of course, in general, you have to go through the infinitely many possible sequences. Answer this question. But we don't have time to go through all these infinitely many differences, and we simplify our task. We use assumptions that both symbols, they independent, and they have the same probability. That for 1 and minus 1, you have the same probability. As a result, in order to understand what happens with the output, you just need to analyze 4 possible pairs of symbols. For first symbol you have. And then you just take all possible combinations. 1, 1, 1, minus 1, minus 1, 1, minus 1, minus 1. So you just define all possible combinations for 2, and all of them, they have the same probability. And if you analyze what will be the output for all these 4 possible combinations, then you get actually answer to what happens with infinitely many realizations. can you take microphone? Where is better?
The output is nothing but the pair convolved with g of n, right?
Yeah, I mean, this is, you take first symbol and multiply by of 0. Then you take second symbol and multiply g of 2. Then you just go through all these products. You have xn minus xn. Yeah, actually what you do in the end, we calculate xn minus xn minus 2. What we do. Just calculate difference between possible pairs of symbols. This is what you get for y of n. But you should be careful because xn corresponds to the current symbol. G of 2 corresponds to its this delta, it's a pulse that corresponds to past symbol. 2 multiplied by past previously received sample. And G of 0 corresponds to sample that we have at the moment. And what is G of minus 1? Example here, f of minus 1. What it is?
0.
Yes, it's 0, but what's the meaning of it? The meaning. I already heard the answer. It's future. It's this impulse response corresponds to sample from future. And because usually you don't have access to future, say that this everything what's in future must be equal to 0. This reason because we name this this kind of filters, these such impulse responses, as causal filters. And for non-causal filters, you have also negative part. But it's non-causal because it assumes that you have somehow access to future.
Why it is x of n minus 2? Is it because we don't?
N minus 2 is past.
Why we have taken?
No, xn is, I mean, you should distinguish G of n, impulse response, and xx of n. This is sample. Future will be xn plus 1. And we also don't have access to future sample. Non-causal. Okay, yes. So please be careful because you have this interesting that you have, if you take wrong parts in impulse response, you come into the future, and till it reaches us, we don't have access to it. Yeah. So any other questions, just let me know. So we have time. Okay, we still have 15 minutes to complete. Now we go to part D. Part D, and we need to specify the second moment. Okay, now we need to find second moment of our output sequence. When I don't know answer, I ask you. How can we find second moment output of the resulting sequence? Just statistically independent. But I mean, how can we find the second moment? There is much easier. I mean, because you already know what the probability mass function. No definition of probability mass function, and have picture of it. And we can use definition of second moment in terms of probability mass function. Okay, expected value x squared is correct. But I mean, here we can use hint because if you look to definition, I mean, how you calculate second moment? You actually, in terms of probability density function, you calculate integral of x of your random variable squared times probability density function, and then we have, instead of probability density function, we have probability mass function. But the algorithm is almost identical. Instead of integral, you will have summation over all possible, and then we have, right, we should write it as y squared times this probability mass function. And you already know everything about probability mass function. And you know what the possible outcomes for y. -2 is. Then we can just substitute everything what we know. Have -2 squared times probability, 1/4, plus times probability, plus 2 squared times probability amplitude, again 1/4. Let's try to calculate the result. It will be 1 plus 1, 2 to 2. At all. What will be the result of our autocorrelation function for 0 point? How? No, that's all actually. All for part D. And now we go to part E. We need to sketch the autocorrelation function of the discrete as well as corresponding power spectrum density. Okay, now we go back to discussion about input signal, x of n. And we need to find autocorrelation function and then power spectrum density. So now, actually, you should tell me what will be the autocorrelation function and how can we find it. Again, I would like to remind you that x of n is a sequence of symbols. Symbol belongs to alphabet, -1 and 1. And say that all symbols independent. That's actually all what you need to find autocorrelation. What will be the value of autocorrelation? Okay, yes, you can write that pi xx of L equals to mx. But then what's the value? No, it's what do you do to find this second moment? Okay, good probability. What's the probability? But you can use microphone, so also people.
So
Sorry?
no, I'm just saying that it's going to be the summation.
Can I put
It's okay. So if it's like this, it's going to be 1/2 multiplied by -1 square by 2.
like this? I mean, that's all. And what we have for any other points? Zero. Yeah, I mean, you have this 1/2, 1 plus minus. You can put square and it will be 0. And I mean, it's that's all what you need to know about autocorrelation function. And then you can easily plot it. Have this at 0, you have a pulse with amplitude 1. This is pi xx L. Or any other point, you have 0. Because you have bipolar sequence. It's bipolar. Okay, we have, yeah, this is our autocorrelation. And calculate the power spectral density. That's right, we have constant level. 1. S over 2. Outside, we just read part. So, fine. And what else? What else we need to find? We have sketched the autocorrelation, power spectral density. Now we go to part F. So we need to find power spectral density equation, power spectral density at the filter output. F, y of F. And then, of course, it's very easy. But yeah, by the way, for previous task, we say that f xx of f equals to what? What's the power spectral density? What's the expression? 1. At all. And for results, phi y of f, we use well-known expression that you just need to take transfer function absolute value squared and multiply by power spectral density of your input, by xx of f. Then if we do, for second part we have 1, for first part we have 4 times sine squared, then we advise what was argument, 4 times sine phi f phi f t0, our argument. So, and this is how our power spectral density looks like. And now we need to find autocorrelation function. Find autocorrelation function. In order to simplify our task, we can do the following. We remember that if you have if let's say you have cosine of 2 alpha, you can represent it as cosine square alpha minus sine square alpha, and then you can write it as 1 minus 2 times sine alpha. And from there, we can say that 2 times sine square alpha will be equal to 1 minus cosine 2 alpha. So, and we can just replace this sine square above by 1 minus cosine 2 alpha. Can represent, we write that this power spectral density function of f equals to 2 times and then 2 minus sine. The task, in the last part of the task, yeah, I forget 2. Want to combine them, I will still write it as 2 times 2 pi f. Then we have hint, 2 cosine x, 2 pi f, 2 times 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 you can see as sum of exponential function jx plus exponential function minus jx times cosine minus exponential function have write it as g f g I, and now it's very easy to calculate Fourier transform and actually find not only Fourier. I should put 2 as g f times 2 function put t 2 at the position of index, because then we do this inverse Fourier transform. Inverse transform for this time Fourier transform. Okay, and then actually we remember that how did we get that? We remember that our spectral density was nothing else as summation goes from minus of autocorrelation function at times exponential function minus j I f goes like this. And now look, we have almost expression that we need to have. Yeah, we can. Oh no, we get to do last step to allow us to find the answer. Finally, I have to write our power spectrum density as 2 times, and then can we represent 2 as exponential function of something? Yeah, exponential function of 0. You can say that this 2 is nothing else as 2 times exponential function g phi f times 0 times t. And we have minus 1 times exponential function phi f. I should put minus actually. Minus in front of j. I should put minus j 2 pi f minus 2 t0 and minus minus 1 times exponential function minus j pi f times 2 times t0. And now you see that actually we can easily reconstruct our autocorrelation function out of this expression. Because you have exponential function, what's the index, you know what's the amplitude in front of it, and following this expression below, you can just construct what's the points of your autocorrelation function. You can say that autocorrelation function y at minus 2. What will be the value of autocorrelation at minus 2? Minus 1. Minus 1. Then autocorrelation at 0. 2. Will be equal to 2. And y at 2 will be minus 1. And that's all. I mean, now you can just plot based on this result. You can plot your autocorrelation function. Phi y of or L. And we get that we have at 0 At 1, it will at 2, it will be 1. At -1, it will be -2. Minus. This is how our autocorrelation function. Exactly 10:30. Okay, that's all for today. It was the last part for task number 4.2. Are there any questions, any doubts? What you like to discuss? Then I would like to wish you a productive day, and we see each other next week on Wednesday. Thank you and goodbye.